I'm Gianni, and this is my thesis, Planning of Operation and Propulsion Maneuver in Satellites based on digital twin and multidisciplinary optimization. So I'm doing an industrial PhD with DNI Space, and I want to start with a really short introduction of DNI Space. That is a company that is working both on software and hardware. The hardware is an electrosprite thruster called Athena, and software is a mission space mobility tool, and is the part I'm working on, and it provides high fidelity flight dynamics propagations. Concerning my PhD, I started my study on low thrust trajectory simulation and design, and I saw some case simplifications that are the lack of integration of power constraints, the neglect of attitude dynamics, and so there was a lack of ADCS model. So that's why in the methodology of my studies, I start my literature review on 6 degrees of freedom ADCS digital twin, and also on low thrust guidance such as QLOW. And in the first part, I start to create the model. So the torque disturbances related to attitude dynamics, such as magnetic torque, gravity gradient torque, and also the torque induced by thruster when they are not in the center of mass of the satellites. And also control laws like PID, and I also found a way to find the right weights using a generic algorithm. And then I started to create the digital twin of the actuators, so the reaction wheel, the magnetorquers, both for the saturation of the reaction wheel, but also for attitude control, and also thruster, both used for positioning and attitude torque. Then I faced the problem that I want to do optimization with 6 degrees of freedom, but it's really computationally expensive. That's why I decided to use adaptive IDCS, so using 6 degrees of freedom just during critical phases, and 3 degrees of freedom only when for the non-critical operations, so in order to minimize the computational load. And I also use a power away guidance that is based on the state of charge of the battery. I started to apply this concept to GTO to geo transfer. And as you can see in this slide, on the left, there is a spacecraft with the yellow one is a null effect thruster with a solar panel, the red one, and 4 reaction wheel in a pyramidal way and in a pyramidal configuration, and a battery. So the idea is to do a GTO to geo transfer, and the problem that I'm facing as different objectives that are the minimization of mission duration, the maximization of leftover propellant, and the minimization of energy draw. And what I'm doing is feeding a generic algorithm with some variables that are the weights of the QLOW, so for the centricity, for the inclination, also the thrust effectivity coefficient, and the state of charge of the battery, both for high threshold and low threshold. And in this slide, I put the schematic of the scheme of the concept of the mission, and I did it for both 3 degrees of freedom and the mix of 6 and 3 degrees of freedom. I will not go in detail, otherwise I don't have time, but I can say that there are 2 main phases. The one where I'm thrusting and the one where I'm coasting, and I'm pointing with the solar panel to the sun. And I'm switching between these phases based on the state of charge of the battery and the thrust effectivity. And there are other 2 phases that are phase of are phases where I'm using 6 degrees of freedom for switching from sun to trust and vice versa. I put some results here. As you can see, there is a Pareto front on the left, where there are the two objectives, the propellant used and the duration. And of course, we have worse results with the mixed degree of freedom simulation, but we are considering our more realistic case. And also, if we analyze one single simulation at, for example, 150 days, we can see the simulation time is for 6 degrees of freedom, for mixed degree of freedom, and also for 3 degrees of freedom. And we can see that we are saving a lot of computational load with the mixed one. Right now, what I'm working on is to dynamically adapt the QLOP parameters and also the trust effectivity coefficient during the simulation. And I'm doing a literature review on the reinforcement learning. And I already created an initial model, and I have some results, but they are not really mature. And the idea is then to do a benchmarking with the generic algorithm and splitting the simulation and optimize with the generic algorithm every single segment. But of course, this is expensive, but it's just for comparison with the reinforcement learning. Other thing that I will try to do is a new concept of operation machine that will be more realistic. And also the application to a real scenario that is the ESA Smart 1 mission that was that is a lunar mission. And in this slide, I put some of the conferences that I attended, and I will present a paper on the ISC this year, and hopefully it will become a journal. And yeah, that's it. Thank you so much. If you have any questions.